Hello everyone. Today, I'm excited to present our work, Benchmarking and Bridging Emotion Conflicts for Multimodal Emotion Reasoning. We begin with the fascinating field of multimodal emotion reasoning. This is the task of integrating cues from video, audio, and text to allow an AI to not just recognize, but also explain human emotions. This capability is vital for creating more empathetic and effective AI systems, with applications ranging from educational assistance to psychological counseling. While current models are powerful, they often falter when faced with the nuances of real-world emotional expression. This brings us to a key challenge we call multimodal emotion conflicts. These are common situations where emotional cues from different modalities are inconsistent. For example, as you can see on the slide, a person might show disappointment or sadness in their facial expression, while deliberately maintaining a calm, neutral tone of voice. Humans do this all the time, perhaps due to social norms or attempts to regulate their emotions. However, as the right side of the slide illustrates, current multimodal large language models, or MLLMs, systematically fail in these scenarios. They tend to over-rely on a single modality, often the audio, and miss the true underlying emotion, leading to incorrect reasoning. To properly study and address this problem, a suitable benchmark is essential. That's why our first contribution is the Conflict-Aware Multimodal Emotion Reasoning Dataset, or CAMR. It is specifically designed to evaluate MLLMs in these realistic conflict scenarios. As shown in the pipeline, we constructed it through a careful three-stage process involving unimodal labeling, manual checks, and majority voting. This allowed us to create three distinct subsets: video-aligned, where the true emotion is in the visual cues; audio-aligned, where it's in the audio; and consistent, where both modalities agree. Using our CAMR benchmark, we investigated why models fail. Our analysis revealed a systematic and pervasive audio bias. To quantify this, we introduced a metric called Unimodal Attention Preference, or UAP, which measures the proportion of attention a model gives to each modality. As you can see in the graph on the left, the blue line representing audio attention is consistently and significantly higher than the orange line for visual attention. This confirms that even when the visual modality contains the true emotion, the model's internal mechanisms are disproportionately focused on audio signals. So, what is the root cause of this bias? Our investigation pointed to a key factor: an extreme token imbalance between modalities. For instance, a model like Emotion-LLM might process 256 tokens for video but only a single token for audio. Because visual information is so high-dimensional, it can appear sparse or noisy, causing the model to default to the more compact audio cues. We confirmed this with the experiment shown on the right. We artificially increased the number of audio tokens to match the video. The results show a clear trade-off: performance on video-aligned data improves, but it degrades on audio-aligned data. This proves that while token imbalance is a major cause, simply rebalancing them isn't a viable solution. To truly solve this problem, we need a more sophisticated approach. Therefore, we propose MOCR, a parameter-efficient framework designed to mitigate this bias and promote balanced modality integration. MOCR stands for Modality-Specific Experts and Attention Reallocation, and it tackles the problem from two complementary angles, one during model training, and the other during inference. First, for the training phase, we introduce Modality-Specific Experts, or MOS. As illustrated here, MOS consists of three lightweight expert modules: a visual expert, a non-visual expert, and an omni-expert. Crucially, their outputs are fused using a regularized modality gate. This gate dynamically adjusts the contribution of each expert on a sample-by-sample basis, preventing the model from developing a static, habitual over-reliance on any single modality. Next, for the inference phase, we introduce the Attention Reallocation Module, or AR. This module addresses the bias that persists in the model's frozen backbones. AR operates with a surgical precision. First, it identifies only the specific layers and attention heads that exhibit an excessive bias towards audio. Then, it carefully reallocates a portion of their attention towards visual tokens, while preserving the original intramodality attention structure. This precision is key to avoiding the performance trade-offs that plague other methods. Now for the results. On our challenging CAMR benchmark, MOCR, highlighted in the bottom row, achieves state-of-the-art performance across all three subsets. Most importantly, it significantly improves the average performance on the difficult video-aligned subset to 35%, outperforming the previous best by nearly 7%. The effectiveness of MOSIR extends beyond conflict scenarios. On the general-purpose MR reasoning benchmark, our model achieves a new state-of-the-art average score of 60.58%. This is a remarkable 9% absolute improvement over the previous leading model, Emotion LIMA, showcasing the strong generalization ability of our approach. Our method also excels at standard emotion recognition tasks. On MER 2023, MOSIR achieves the highest F1 score of 0.9027. Furthermore, on the large scale, in the wild DFEW dataset, it sets a new state-of-the-art with a UAR of 64.26%, outperforming even specialized single-task models. Finally, our ablation studies confirm that each component of MOSIR is crucial to its success. In Table 7, we compare our AR module against a previous method, PAI. Notice the arrows. PAI improves video-aligned performance but at the cost of degrading audio-aligned performance, a classic trade-off. In contrast, our AR module yields consistent improvements across all scenarios, proving it successfully resolves the bias without introducing negative side effects. In conclusion, our work makes three key contributions. First, we identified and analyzed the systematic audio bias in MLLMs that hinders performance in emotion conflict scenarios. Second, we introduced the CAMER benchmark to facilitate further research in this critical area. And third, we proposed MOSIR, a novel framework that effectively mitigates this bias and enhances overall reasoning, leading to state-of-the-art performance. Thank you for your attention.